First of all, thank you all for coming tonight. I might know one or two of you. What I want to talk about is something that a small team of us have produced, which is exactly what that slide says. It's the Chem4Word tool, which is a plugin for Microsoft Word. And it's all to do with C#, chemistry, and citizen science. It's something that we've been working on for about 10 years now. So that's what getting on for 10 years on and off. So let's crack on with the talk. First of all, like I say, well, I say 8 years. It's probably more like 10 years. There's a group of about 3 of us, and we've had a few ringers come in once or twice with us. But basically, there's a core team of about 3 of us, and we've been supporting this plugin from Microsoft Word for about 8 years now. Yeah. So I think the first thing to do is meet the team. First of all, is me. Mike Williams, who's also with us tonight, and I don't think Andy can be with us tonight, but we are basically Chem4Word at the moment. We haven't been in the past. I didn't start the project. I just took it over, and Andy and Mike joined and been helping me since. So something about me. I did have a PhD in chemistry. I spent about 18 years in informatics in total. On and off. I'm now with the University of Nottingham, which is where I studied. But I have spent about 14 years at AstraZeneca and another 4 years doing other informatics work here. Now, I don't do any informatics at all now for my job. I'm just a systems analyst. Mike is a veteran programmer. He's got 36 years of programming, started off basically in low-level languages. He's not a chemist, but he's learned an awful lot more chemistry than most people would be able to do. And then we have Andy, who also has a PhD in chemistry. He spent 20 years at AstraZeneca, and he's been working for about the past 10 years as an independent consultant. We all worked at AstraZeneca together. We all took redundancy, and that probably shut the site down, and we've all gone our separate ways, but we came together to work on this particular project. So let's look at it. Okay, this talk really is about chemistry and computing, and it's probably not the two things that you think would go together quite well. If I were to ask you really what you think chemistry and computing means, you'd probably be inclined to say, think about molecular modeling, a modeling of biological targets, proteins, enzymes, that kind of thing, the sort of thing that you'd really want to interact with in a drug molecule. And that is very, very important in research. More recently, you might be thinking of Professor Sir Martin Polyakov, who did the wonderful periodic table series of videos, a completely interactive periodic table. You can click on an element, and it actually shows you a nice little video showing what each element does, why it's important. Give Martin a plug, because he's actually a friend of mine, and I'll give him a plug wherever I possibly can, because I think he's done a wonderful thing here. But that's not really what Chem4Word is about. And what Chem4Word is about is really the language of science, and how do you capture it and bring it all together. I mean, how do scientists communicate? They communicate in print mainly, right? So they produce documents, and these documents often get published. Or if you're a teacher and you're actually teaching people, I mean, you'll produce materials. Or if you're a student, then you might want to do a sort of classwork assignment. So I'm going to take a bit of a diversion here, and I'm going to talk about what the language of science used to be. And as an example, I'm going to completely go out of chemistry at the moment. I'm going to talk about the ancient Greeks and the use of rhetorical algebra. Now, rhetorical algebra, the most famous example I could think of at the moment is probably this one, which we all know, which is Pythagoras' theorem. The square on the hypotenuse is equal to the sum of of the squares on the other two sides. Everybody knows that, right? But people don't tend to communicate like that nowadays, especially not when they're trying to get concepts across. They communicate symbolically. And this is an example of Pythagoras' theorem, actually done symbolically. A squared equals plus B squared equals C squared. It's concise, yeah? It's a lot less verbose than this stuff at the top. And it's intuitive. You can look at that and you know exactly what whoever it is put it down is trying to get across. You'd otherwise have to know what a hypotenuse was, for example, and that you're actually talking about a right-angled triangle. So I suppose the question now is it possible to do the same for chemistry, to communicate concepts like this symbolically in chemistry? And the answer is, well, let's do a comparison. This is rhetorical chemistry, which is really what you would read in a journal as part of the text. Now, that probably doesn't make much sense to you. And to a non-specialist chemist, that wouldn't make much sense to most people. That is, in fact, a reaction which I did many, many years ago. Burned into my brain, I have to say. But really, symbolic chemistry, which is supposed the equivalent of symbolic algebra, looks like this. You've got a molecule on the left-hand side here, and then you're subjecting it to chemical reaction. And up here, you've got your reagent, which is called thionyl chloride. And down here, you've got solvent, which is dimethylformamide. And they've both got abbreviations. And then it produces the molecule on the right-hand side. And that is exactly the same as what's being said at the top of the slide in English. Well, chemist's English, let's say. So really what Chem4Word is about is bringing this kind of stuff into Word and doing it in such a way that we can capture the information that's in there. So I'm just going to take a little diversion here in order to try and simplify exactly what the symbolic language is about. And I call this getting rid of the foliage, really, but this is how chemists talk to each other. We tend to represent molecules as diagrams, and in these diagrams, a carbon is a vertex or a corner of a connected network, and hydrogens are implicit. We don't actually draw them out. So carbon atoms, we don't put a C there for them. Hydrogens, we just don't draw them at all. So this is like a defoliation. This is benzene on the left-hand side, if you don't recognize it. It's a ring of 6 carbon atoms. And then we put it through this defoliation sort of operation. And then on the right-hand side, we get what looks like a benzene. This is, in fact, how a benzene ring is actually written out. If you were to pick up a chemistry textbook, you would see that on the right-hand side far, far more often than you would see the notation on the left-hand side. So let's talk about how Chem4Word started. Like I say, I didn't start it, but the chap on the left there is Peter Murray Rust, who's, again, another friend of mine. The reason I got to know him was through working on Chem4Word. And in Microsoft research in Cambridge, Tony Hay, who was the director at that particular time, was approached by Peter, and Peter said, I've got this really good idea for this open source project. And hopefully we can open up the scientific literature somehow in doing this. Will you fund it? And Tony Hay said, yes, I'll fund it. And that's how it was born. This is back in about 2011. After I left AstraZeneca, I did a stint contracting, and I got a contract down for about 8 months working in Microsoft research. And I was introduced to Chem4Word. And what subsequently happened was the guy who was leading the project said, I'm bored with this now, I want to go off and do something else. Can you find something else to do it? And I said, oh, right then, because I knew that if we didn't do anything with it, it would die. So offered to take it over, and I managed to round up the usual suspects as it went, and get Mike and Andy involved, because I need both of them. And ever since then, we've been maintaining it and looking after it. So let's talk about the add-in itself. So what is it? This is really what it is. It happens to be a plugin for Microsoft Word, which adds a toolbar. Now, as you can see, I'm actually running the debug version here at the moment. But what the toolbar does is it brings in a whole load of functionality into the desktop version of Microsoft Word. I would say it's the desktop version, not the online version, because the online version of Word is a completely different beast altogether. So this is the chemistry that I was alluding to earlier, except it's a bit more involved now. And what we've got here is something that I've drawn out, which is the reaction I was talking about earlier. And I've added a bit down the bottom here, completely typo, that I shouldn't be in there, of how you actually make the molecule from scratch. And believe it or not, I've done this. It shows the various stages of conversion that the molecule goes through in order to get the end product. That's a reaction sequence. So, like I say, it's free. It's completely open source, so anybody can download it and use it. They have to pay anything for it. It's written in C#, and it uses WPF, and it uses Visual Studio Tools for Office, which is the Microsoft proprietary framework for integrating .NET applications or .NET add-ins with Microsoft Office. Doesn't just work with Word, works with Excel, works with PowerPoint, right across the whole ecosystem. Very important part about this add-in, and I can't stress this enough, is it uses a combination of Office Open XML, which is the document format obviously used for representing a Word document in the background. Embedded in that is a dialect of XML called Chemical Markup Language, or CML for short. That was invented by Peter Murray Rust, and it was probably the first actual practical application of XML in terms of creating a dialect for it. So this is really quite groundbreaking. This really was quite groundbreaking stuff when it came out. Say it was done in 2011, so it's been around for quite a while here. There's been about 3 versions of it since then. We have, since version 1, all subsequent versions have been produced by our team, and it handles structures and reactions. Chemistry is a science of change. Basically, you can draw a molecule out, but what people are really interested in is how do you turn that molecule into something else? And what we're seeing down here, chemical reactions, one molecule being transformed to another by subjecting them to reagents and conditions. Reagents above the arrow, conditions or solvents below the arrow. I'd say it's just quite important, actually. We release it under the Apache 2 license, not GPL. GPL is completely incompatible with the Microsoft ecosystem, but Apache is a much more permissive license, and it also allows nice things like, say, if we wanted to commercialize certain aspects of the product later, we can do that without violating the license. It does, however, tie our hands in a certain way, because there are a lot of chemical toolkits out there. There's even a couple in .NET, for example, but they tend to be GPL, and GPL and Apache 2 are really quite incompatible. So we've had to roll our own in terms of chemical toolkits. And this, I think, is the most important thing here. This is something I'm going to come to later. We've all heard of the semantic web and what it involves. It involves attaching actual meaning to the stuff that we see on screen somehow, so we can meaningfully interrogate it afterwards. What we're talking about here in Chem4Word is semantic chemistry. what you see drawn out on screen is in fact completely semantic in the sense that you it has context attached to it. It's not just a series of metafile function calls saying, can you draw this line here, this squiggly line here, this bit of text here. Underneath the underlying data is completely meaningful and human readable and actually means something. So let's look at semantic chemistry. The field of chem informatics that is actually doing chemistry by computers is big business, and I mean really, really big business. And projection is it's going to grow to $21 billion turnover by 2024. And that is an awful lot of money. It'd be nice if you could get a piece of that, but I don't know how you do that with a free tool. I'm going to show an example of a commercial product which has been around for quite a while now, probably about 20 years, called BioVia Draw. And what BioVia Draw looks like is that. That is being used to draw a molecule called indole. Indole is quite notorious because it's notoriously smelly for one thing, but it's really looks like the sort of stuff that we've got for Chem4Word. And what you would do normally is you'd fire up this tool, you draw your molecule out, then you copy and paste it in, and you get an Olay embedded object in your Word document. But the way it's represented in the document behind the scenes is complete gobbledygook to most of us. It's a whole load of binary information. You can export it to a text format. And this is what the text format looks like. And that's not much better, to be honest with you. And this is called a mol file, and it's a proprietary format, and it's under the control of the vendor. And if they want to change it, they can do that, and they frequently do. It doesn't really say very much there that it can be easily read or understood. And this is a persistent problem throughout the entire chem informatics industry, is that each vendor goes off and produces their own format. So really, it's like the Tower of Babel being struck down. The situation really hasn't improved. I'd say, if anything, it's got worse. So you've got all this information that's actually locked up in a proprietary format, which has most of it has to be binary and impossible to get to. But Peter Murray-Rust came out with this axiom. He's a bit of a force of nature in the world of open science. He basically said, if you're free to read a document, then you should be free to actually mine the information in the document using automated tools and extract information from it. So freedom to read should be freedom to mine. And he came up with his own answer, which was chemical markup language. And what chemical markup language looks like is, in fact, this. It's just purely XML. But you can see here, there's some XML namespaces, for example. But you've got here, for instance, this description of a molecule. There's a whole load of formulas down there, and they're each given their own particular context. They probably don't mean too much to you, but they would mean something to a chemist. And you've got down there all the names by which the molecule is known. And there's only one actual name that's missing from there at the moment, and that's the name aspirin, because that is, in fact, the description for an aspirin molecule. So it's extensible, parsable, and human readable. And like I say, the first domain-specific application of XML. This stuff down here, aspirin array and bond array, that describes the connectivity within the molecule, how it's actually put together. Yeah. And there you go. That's what it's like when that's actually read by our tool, which is Chem4Word. So that is aspirin. That's what you take when you've got a headache. So I'll tell you what, let's actually fire up aspirin for now. I'll just put that there. So this is me. I've actually been playing around with Chem4Word. You can all see that, can't you? Yes.
Yep, we can see that.
Okay. So this is the toolbar up here. So what we can do is we can search a public repository. If I might want to write something, aspirin is a common and cheap anti-inflammatory. Yeah. So I'm just typing out stuff in Word at the moment. Aspiring, aspirin actually. So I'll do a search here, and up pops this little window. We're searching a publicly available database of virtually every chemical you can think of. So click that. This comes back. This is a list of all the chemicals with the name aspirin in it, but we'll just go for the top one because that looks like what we're looking for. And we click import. That probably I should move down. Hang on. Let's do that again. Get rid of these. Okay. So I'll just do it again. So search for aspirin. Spelled it. Okay. So I can type down here. This is aspirin. So Chem4Word has just gone to a public database, done a name search, pulled back a structure, a chemical structure, yeah, and rendered it in the document. Now it does this using drawing ML, but if we wanted to, I could draw it from scratch, and we provide full drawing functionality in Chem4Word. This is our editor called Acme. I'll cover that a bit more later. So the first thing I'll do is drop in a benzene ring, and then I'll draw a bond, and hang on, let's make this a bit neater. So I'm basically just drawing the skeleton of the aspirin molecule at the moment. And then I shall edit these atoms. Well, that is aspirin drawn out from scratch. Yeah. So this is an editor that we've written, which basically draws molecules for you. And again, you can see the syntax here that I was referring to, where we hide the hydrogen atoms. We can add these in, for example, just get rid of them afterwards. We can do other things with this, for example. I mean, I could take a copy. I can paste the copy in. If I wanted to, I could join these two atoms together. I mean, there isn't a particularly good reason why I'd want to do that, but this gives you some sort of feel for what Chem4Word is doing. So we give people the ability to search for molecules, draw them. This is something that it does. It's just going off and just checking to see if the molecule can be matched in a public database. It can. It's come back with that name. Okay, so it's effectively the same molecule there and there. Chem4Word does a couple of other things as well. You could import from files, but I'm not going to do that. We have here on the left-hand side this thing which we call the library. Now, at the moment, Chem4Word ships with the standard library of about 2,100 chemical compounds. These chemical compounds were very kindly given to us by Peter Murray Rust as part of a project he was working on to do with essential oils in plants. So this library component down here, I'm paging through this, and in real time, what it's doing is it's sucking back the underlying CML for these structures and rendering them. And we can easily paste a structure in the molecule. For instance, menthol, very, very common molecule used in various things. For instance, if I want to put menthol in, then I can just paste it in. It goes straight in. So we've got the ability to provide a whole load of pre-made compounds. The user can add compounds to the library as well. I'm not going to show that at the moment because it'll just clutter this library up. I don't want to do that. We also have got something which we call the navigator. And what the navigator does is it shows instances of chemistry actually stored in the document. Now, this chemistry is stored as CML within what we call custom XML parts. It's a standard word feature for hosting foreign data within a document, so it can easily be retrieved. Yeah. So if I click on there, for example, and then I click that arrow there, it's saying, right, well, find me an example of that chemistry. Yeah. Or if I click on this arrow here, it's just found the aspirin molecule. So if somebody's got a big document, they've got a lot of structures in there, they can easily resolve it. Yeah. The last thing I think I'll show you is the ability to see the underlying CML. So if I click on that button there, then that shows you the chemical markup language, which is pretty much identical to what I showed you beforehand for that molecule, even if it's drawn from scratch. Because it's semantic and because we have the ability to store lots of different heterogeneous information there, we have a show as button. So this shows the various names that we've got down here. At the moment, we've got the 2D representation of aspirin, but there's a whole lot of other stuff down here. I wouldn't expect it would mean very much to you. But for instance, if you just want to show the formula, show it as the formula, you can do that. If you want to show it as what we call the IUPAC systematic name, then it'll do that as well. So this is really quite a powerful tool for putting together documents. Okay, right, let's go back to my presentation, shall we? Okay, so where were we? So who uses Chem4Word? Well, this is who uses Chem4Word. These are all, we have telemetry built into the program, and it just does a basic monitoring and basically says, you know, who's using it, where are they? We make a sort of, we try and find out as much as we possibly can without actually infringing intellectual property. For instance, one thing it doesn't do is it doesn't capture the chemical structures that people are working with. It just captures the basic operations. Yeah. So this is where it's used all over the world at the moment. And it is literally used all over the world. I think we've got somebody in Greenland, and quite a few people in Reykjavik. I don't know what that island is. They haven't got a clue. So very, very popular. We've had 540,000 downloads of this tool during its lifetime. So it's surprising how many people, how many chemists are actually out there. If you want to do this kind of thing. The colors are different versions of Word. The orange is the most recent version, but we have versions going back to 2013, even 2010 in certain circumstances. And it's becoming more of a challenge to try and support those. And it really teaches students and scientists to actually use this. Professional and academic chemists tend to be very conservative in terms of the tools that they use, and an awful lot of that's to do with the fact that the institutions that either employ them or host them have got bulk deals with informatics suppliers. So they'll use what they're told to use. As individuals, or teachers who, let's face it, can't go out and afford to spend a few £100 on a version of something up by their draw. They've got a free tool, they'll use it. So let's get on the interesting bit. Let's actually talk some tech, shall we? Let's talk about how it works. Well, I mentioned Visual Studio Tools for Office. We won't dwell on that so much. It's just a very handy framework for integrating toolbars and action panes and all sorts of things with Word. But you're probably more interested in how is it that you get the chemistry to show interactively in a document. Well, first of all, we have to start off with a chemical markup language. That's what underpins the whole of Chem4Word is the CML. What we then do is we upload the chemical markup language into an in-memory model, and I'll come to the model later. Okay, but the model basically underpins everything. Now, for the interactive part of it, which actually uses WPF, what we do is when we're displaying a structure interactively, we use drawing visuals in WPF, which are very, very lightweight objects and very, very quick to draw, hardware accelerated. You saw the speed at which those structures were being drawn. That's mainly down to WPF rather than anything that we've really done. When it comes to editing structures, then we have something called a controller. So it's basically a model view controller architecture. And the controller manages the model and responds to user commands. Commands are in fact implemented in WPF as commands. So when you saw me drawing things like chains and bonds and rings and that kind of thing, that's what I was doing. I was interacting directly with WPF commands, and behavior switch the editor from different modes, for instance, like from ring mode to draw mode, depending upon exactly what it is that you actually want to draw. To give visual feedback, you may notice that there was some orange highlighting going on when I was drawing stuff. We use adorners for that, which are a special kind of framework element in WPF. Now, in the document, and I have to say, this is not my area of expertise, this is Mike Williams' area of expertise. We have custom XML parts, and these are these store the CML, and then these talk to content controls, and the content controls contain drawing ML, and in order to actually produce the drawing ML, we have to use a renderer. So the renderer is in fact actually converting the CML, which is stored in the custom XML part, directly into drawing ML, which is displayed in a Word content control. It used to be a bitmap. It was horrible. We changed that. So, I mean, how do you model a molecule? Because I mentioned the model, and there's got to be a logical way of actually representing a molecule. Well, there is, and it's really based on the world of mathematics. Now, what we use a graph, but I'm not talking about a graph in terms of pie charts or bar charts or anything like that. I'm talking about it in its mathematical original sense. And a graph happens to be a whole load of vertices and edges. A vertex is a point on a graph, a node, and an edge connects the vertices together. In what we're talking about here, we're talking about an atom represents a vertex, and a bond is in fact an edge. So it's a really ideal representation that we've got here. And again, our old friend, the benzene molecule, you can see here what we've got here is we've got carbon atoms and hydrogen atoms, this time bond stick representation. And we have, on the right-hand side, the various nodes, which are the vertices, and the bonds are the edges. And that is exactly how it's actually done. So the atoms we store in a dictionary, a C# dictionary, which we key by various labels. And so for some reason, all right, okay, it still doesn't come up now. bonds are slightly different. Bonds are stored as a list, and for each molecule has an edge list. So each molecule's got its own atom dictionary, and each molecule has got an edge list. And an edge list basically says, this is the start atom A1, this is the end atom A2, A2, A3, etc. And going around like that, you can build up the molecules. So you provide your atoms first, and then you say how they're connected. The great thing about using an edge list is if you're doing any copying or pasting, it's really, really easy. If there are different ways of representing various things, representing molecules in different ways, but this is by far the most convenient way that we found of doing it. So the model itself, at the top, we start off with a model object. These contain various molecules. So a molecule can actually contain another molecule, which does complicate things for us somewhat. But a molecule really consists of a dictionary of atoms and a list of bonds, which is what I've been talking about. We also talk about reactions, and this is something that we just added. A chemical, each model's got a reactions collection, and this consists of a whole load of individual reaction objects, and each reaction has got a list of reactants and products, and these are just references to molecules. And we've also got annotations in there if somebody wants to put some text in. So I'll talk about algorithms now, because these are actually quite interesting. As you can probably imagine, this is a really algorithm intensive area of information science. And I can't cover all the ones that we do, but I can just touch on the sort of challenges that we're up against at the moment. Rings of atoms in chemistry are incredibly important. For one thing, if you look at a drug molecule, drug molecules have got to be in a certain structural conformation to be active, to lock into an active site of an enzyme or receptor or something like that. So as soon as you put a ring in, it actually confers some structural stability. Rings radically change chemistry. Benzene behaves in a way that other organic molecules don't. Its chemistry is very, very different. And rings must be represented correctly. Now, we'll come back to benzene again. On the left-hand side, there is the right way to draw a benzene ring. A benzene ring is generally drawn as a set of alternating single bonds and double bonds. A double bond is just a bond repeated between two atoms. The left-hand way of doing it, you draw the hexagon first, and then you draw the subsidiary bonds inside the ring. The right-hand way of doing it is very wrong. Now, to be able to do that, we've got to know, first of all, what the inside of the ring is and what the outside of the ring is. But we also have to know where the rings are, first of all, to be able to do that. So, well, this is an example of an algorithm that we do that we use extensively in Chem4Word to make the molecules look right, because actually the model doesn't tell you. It just tells you there's a double bond between two atoms. It doesn't tell you where to put the double bond, whether it's on one side of the single bond or the other side of the single bond. So we've got to work it out. So what the Figueras algorithm does, it was invented in about 2003, is it does ring perception. And it's really three stages to it. In order to be able to work out where the rings are in a molecule, we start off with a very simple formula. This is the Euler formula discovered by the great German mathematician. many hundreds of years ago, well, not many, a few hundred years ago, I think. And he basically worked out, he said that the number of cycles in a graph, or R, is equal to the number of edges minus the number of vertices plus 1. Well, in this particular case, the number of rings is equal to the number of bonds minus the number of atoms plus 1. So that immediately tells you whether or not you've got rings in a molecule. And then what we do is we take our molecule, and when I say degree here, the degree of an atom is a measure of how many other atoms are directly bonded to it. So a degree 1 atom has got one other atom bonded to it. A degree 0 atom's got no other atoms bonded to it. Degree 2, 3, etc., so on. So we can start off. We can actually start off with a basic molecule, and we do a pruning operation. What we do is we successively remove the degree 1 atoms until you've got nothing left but degree 2 or higher atoms. This is the pruning operation we've got here. And then we do a breadth first search. So what this does is we've got this core of the molecule, and we build up paths. We start off at, say, atom A1, and then we build up paths to all successively by scanning outwards from the atom by atom. And we store the paths against each atom, and as we go round, the paths get longer and longer and longer, and until, for example, if we start off from A5, A4, and we say go and look at the next atom, we might find an atom that's already had a path assigned to it. And in this particular case, if we do that, we know we found a ring. We can add together the two sets of paths and include A1 in it, and those are all the atoms in that particular ring. So it's very quick. Actually, it only takes about 5 milliseconds for testosterone, and this is what testosterone looks like. That's got 4 rings in it. So it's got 3 6-membered rings and 1 5-membered ring. So this is an example of what the sort of things that chem informatics has got to grapple with. And it gets worse, if you can believe that. But there's an awful lot of very, very sophisticated and very, very specific algorithms that have been developed specifically to deal with the challenges of having to represent chemistry in a computer. So we're going to take a look at molecule editing because this was a real problem for us. The first version of Chem4Word didn't actually have a proper editor to it. It had a tool which just allowed you to tweak. All you could do is download molecules from PubChem or other sources, search for them, download them, embed them. You really couldn't draw things from scratch. So what we did was we incorporated a third-party editor, which was ChemDoodle Web. Now that's actually a GPL product, and this is what ChemDoodle looks like. It's written in JavaScript, and we had to embed it in an Internet Explorer control in a Windows form. It's very nice, actually, the things you can do with it, but it's not our editor, and the sort of things that we wanted to offer with it, it was dual GPL licensed and proprietary product. You could go out and you could buy the full fat version of this, or you could use this web version. And because it was GPL, we had to really sort of ring fence it. We had to host it in IE. It's written in JavaScript, so that causes immediate compatibility problems with Chem4Word, which is written in C#. And we had no control over the functions, or we couldn't add chemical reactions, for example. That's something we'd be wanting to do really from the year dot. So we were really limited in terms of the things we could do. The other problem was all the chemistry came back in JSON. So we had to convert from JSON to XML. The thing about JSON is it doesn't allow namespaces, so it's not extensible, and that made it extremely difficult to customize. So what we decided we needed an advanced CML-based molecule editor. We'd have to write our own, and so we called it Acme. Roadrunner jokes. We've been trying to work Roadrunner jokes into the project for ages now, with limited success. But really, we produced Acme, and this is what Acme looks like. It's again Apache 2 license, not GPL license. So that gets rid of one particular problem. It's a native WPF control. What you're seeing here is you're seeing it being hosted in a form, but the bit that really is Acme is the two toolbars and the drawing area. The OK and cancel bits, they are just the hosting form, but you could drop this into any WPF window and use it. It's got a model view controller architecture, and this means that it's hopefully fairly easy to understand how the thing works and to customize it. We have complete control over Acme and the source code. We can do anything we want with it, and it's really a matter of time and resource to be able to produce this. Our hands are not tied by any licensing considerations whatsoever. It's extensible, which means we can plug things into it. And the thing about Acme is, okay, when we draw things, and you saw me drawing aspirin earlier, it's doing everything in the in-memory model, but that is very easy to map to CML afterwards. So we're producing semantic chemistry at the end of the day. I'd like to sort of wrap up here, just talking about what the future brings for Chem4Word. There's Microsoft's ever-changing developer story, which is rather wearing, to be honest with you. I'm sure we've all been at the sharp end of this. First of all, Microsoft decided that they didn't like WPF anymore. Apparently, there's a big political story behind that. So they decided to bring the Universal Windows platform, and developers hated it. Let's be fair. The people have produced UWP applications, but it's really not caught on, and it's quietly being sidelined. So then we've got stuff like Electron, which is used in Microsoft Teams, for example, and that uses HTML and JavaScript and to produce a desktop application rather than something running in a web browser. And now we've got WinUI 3, which is meant to bring everything together. And then finally, just to complicate everything even more, we've got Blazor. We really don't know what to do with this. It's a bit of a zoo, to be honest with you. It's really quite an intimidating prospect, having to try and migrate from WPF legacy code to this, for example. What do we choose? I don't know. And then we've got the problem that Microsoft decided that they don't like the Visual Studio tools for Microsoft Office anymore. So we're left with a load of legacy C# code. The framework itself has been deprecated. Microsoft are not going to migrate VSTO over to .NET Core. And the documentation is not great either, to be honest with you. And then on the other hand, there's the new Office add-in model. Sorry, that should have come up beforehand, which is we wanted to carry on keeping things in C#, We've got everything in the Office add-in model is in fact supposed to be JavaScript. The framework itself is limited in terms of what you can do with it, and believe me, it is a pain to debug, as Mike found out firsthand. So we really are in the proverbial place between the rock and the hard place. That's where we're stuck at the moment. If we stay where we are, it'll probably be obsolete. If we migrate it, it's going to be chucking everything away and starting again. So I was going to say what we're looking for, techie perspectives. If anybody can act as a guide to try and help us navigate our way through this quite bewildering landscape, then that would be really, really useful. So I would say is what we really need is volunteers, to be honest with you, to help us do this. You don't need to be a chemist, believe me. We've got enough chemistry on this project. What we really need are techies. So anyway, this is the Facebook group that we have. We've also got a Twitter feed. You can email us directly. And if you just want to play with the code, it's on GitHub. You can download it, you can play with it, you can compile it, you can pull it apart. We don't mind. Okay. So at the end of it, what I would like to say is thank you to these people, the .NET Foundation, who've supported this project by giving us tools, mainly MSD and enterprise licenses. Very useful they are too. Also, as you're hosting, code signing is very, very important. Just general support in terms of legalisms and things like that, license issues. Microsoft Research, who actually kicked the thing off with Peter Murray Rust in the first place, and also JetBrains have also been very nice, giving us ReSharper. So I think actually that is me done.